All right, hello and welcome to everybody to episode 10 of Technically Speaking. Today we're going to get into the depths of the conversation around dew points, kind of an advanced psychrometric discussion today as we get kind of into an alternate way to look at psychrometry as opposed to the temperatures and relative humidities and dew points that we most commonly use when we have those conversations. So it'll be a fun ride today. Be a little technical, but and again, it is Technically Speaking. So with that, let's go ahead and get underway. As we get moving, a couple of quick housekeeping things. Remember that we don't use the chat in Technically Speaking. We use the Q&A tool. So as we're going through the presentation today, make sure you open up that Q&A tool and drop in any questions that you've got, and we will address those at the end of the session. So with that, let's go ahead and roll into it. Technically Speaking, episode 10. As typical, my name is Brandon Burton, and I am your host today. I am the Senior Principal of Industry Relations at CoreLogic and NextGear. I'm also the chair of the ANSI ICRC standards. And as I've expressed a few times in previous episodes, I'm really here to support you as an industry with standards and with the kind of technical liaison into a number of different conversations. So if at any point I can be of assistance, please keep my contact information, which you'll see on the last slide, and reach out anytime I can be of support. So with that said, let's jump into it. The biggest thing I want to start with today to get us into the conversation around dew point is to talk a little bit just about water at the molecular level, what it is, what it does, how it behaves, because it's really critical that we understand kind of the underlying physics, if you will, the physical principles of water. And to illustrate this, I've got two molecules on the slide, one on the left and one on the right. And these are what water molecules look like when we draw them out as a model. You've got one really large atom and two very, very small atoms. That's why we call it H2O, right? Two hydrogen atoms and one large oxygen atom. They each combined would make up a water molecule. And here we have two of them. I want you to observe the one on the left for a minute. So on the left-hand side, we see that this molecule is moving, right? And matter, unless you're at absolute zero energy, all matter has a certain amount of movement associated with it. That movement can be increased, it can be decreased, and that movement, the sense that we get, the feel of that movement we get is temperature. All right, so when I put my hand on a surface and that surface feels, let's say it feels very, very warm. The reason that surface feels very, very warm to me is because of the combined kinetic energy of all of the atoms and molecules that are moving in that substance, whether it's an air mass or a solid or a liquid. If I feel a warm temperature, then all of that movement, if you imagine this molecule making impacts on the side of something, all of that movement is transferring energy. And that transfer of energy gives me that warm sensation. The opposite occurs if I feel something cold. If I put my hand on a very cold surface, then what's happening is that all the molecules that make up my hand are actually moving with more kinetic force and energy than the surface. And I'm losing energy to that surface. And I'm making those molecules speed up in the process. So temperature is this kinetic energy. And to further illustrate that, I'm going to get the other molecule in motion here. And notice how this molecule of water is moving much faster. The difference between these two is their temperature, right? The one on the right-hand side is a higher temperature, and the one on the left, or the left-hand side, is a lower temperature. It's really important to understand that at a molecular level, this really, really basic element of physics, because it plays a huge part in everything that we do in water mitigation. When we have moisture absorbed into materials and we're trying to remove that moisture, one really, really key element is the amount of energy that moisture contains. And without any, I can't remove the moisture, at least not at any reasonable rate and not with typical processes. So we must have a certain amount of energy present. And part of the reason I'm excited to dive deeper into dew point today is that dew point is a really easy way to understand if there is enough energy present in a system to support drying. And that's one of our primary goals today. We've discussed it a little bit in some previous Technically Speaking episodes. We've kind of broached on the surface. Today, we're going to go a little bit deeper and better understand why dew point is such an important tool. To the extent that I would actually make the claim that if we understood dew point well enough, you wouldn't even need grains per pound, right? Grains per pound is a measurement we've historically and traditionally used in this industry, but believe it or not, you could replace grains per pound with just dew point. and consider all of your drying documentation in just dew point, and walk away with a much better understanding of what's happening than grains per pound. Grains per pound is a pretty odd measurement, and we've talked about that in some pretty extensive detail in previous episodes. So to further understand this, let's take another kind of zoom out a little bit, take a more macro view. So here we've got 3 water molecules that are all moving through this space, zipping through this space. And this is more what it would actually look like as a gas. So water in a container, let's say we have a small container, there's a certain amount of water in that container. At a high enough temperature, these molecules are moving so fast that they're a vapor. And the reason they take this state is because they're moving with so much energy that even though there's an attraction between them, there's an attractive force, the energy, that kinetic energy of their movement is greater, and it overcomes that force and prevents them from bonding. Right, and that's one of the key lessons in what we're going to talk through today, is it's all about the water molecules bond. When water molecules do bond, they're not a gas. I can't remove them from that material through the process of evaporation. They condense into a liquid, they stay as a liquid, they don't necessarily transport through air, and all these traditional means of drying just don't work if there's not enough energy to break those bonds. So again, this is temperature, right? And the greater the temperature, the more likely these bonds are to break. And this principle applies to more than just water, right? It applies to every substance in existence. When we increase the temperature of a substance, we move through changes in state from a solid to a liquid to a vapor. And we could talk about a couple of other states if we wanted to, but those are the ones that we're most familiar with. So now kind of zooming out a little bit further, with water specifically, if we are below 32 degrees Fahrenheit on the far left-hand side, then water does something really interesting. The energy state is so low that the structure of the bonds and the molecules enter something we call the lattice state. And it kind of makes this rigid, solid structure, right? And if I were to keep adding water molecules to that, you'd understand why we call it that lattice structure, because it literally looks like it. But that lattice structure forms a solid. The bond is making a continuous loop, if you will, and that adds some rigidity, some structure to that bonding of molecules, and that's why we call that a solid, right? So this would be the form of ice. What's interesting is that even at 32 degrees and lower, when we have ice, it's still possible to have some vapor in that same environment, as long as the molecules are far enough away, as there's not so much pressure to bring them together, as long as the molecules are far enough away that the attraction doesn't bring them together, right? So you can still have ice and vapor, but what you're not going to have below 32 degrees is ice and liquid. Because if you had liquid, then the molecules are close enough together that you're going to form that solid lattice structure. All right, so you're not going to find a mix at 32 degrees or lower of solid and liquid. Once we get above 32 degrees and we get above that freezing point, then we get a mix of liquid and vapor, right? So we go from a solid and vapor up to a mix of liquid and vapor. And the reason we move into this liquid state is that there's too much energy and too much movement for that chain to become a lattice, right? So there's just enough to break some of those bonds, but not entirely. And we end up with these random chains of fluid or flexible mass. And this is what we call liquid water, right? And again, in this state, there's still a potential for some vapor also to be present. It all depends on the proximity and the amounts of energy between 32 and 212. The more we move to 212 degrees, the more of it's going to be vapor. The more we move closer to 32, the more it's going to be liquid, okay? And then finally, above 212, we become fully vapor. It is not possible, at least at atmospheric pressure, it's not possible to have a liquid above 212 with water. So again, the reason I get into this, and some of this is going to sound really familiar, even if you've just read the back of a box of macaroni and cheese, but and boiling temperatures and all that kind of good stuff. The reason I dig into all of this is because it's really important before I get into dew point that we understand just how critical temperature is to the state of water. It's really important to understand that relationship. As a side note, by the way, this is all stated at standard atmospheric pressure. When we change pressure, these temperatures also change. It's called a pressure-temperature relationship. I'm not going to dig real deep into that today because we'd have to get really deep into even things like refrigeration theory to really understand that. Just understand that at higher temperatures, more energy, more likely to break bonds. At lower temperature, less energy, more likely to attain bonds, right? So with that stated and that said, let's now take a look at dew point temperature. So dew point temperature is the temperature at which, this is the literal definition, the temperature at which air becomes saturated with water vapor, right? The temperature at which air becomes saturated with water vapor. It's a little bit of a mouthful, can be kind of difficult to understand at first, but that definition is going to make a lot more sense once we analyze it on the psychrometric chart here for a second. Okay, so here we have a psychrometric chart in front of us, and I'm going to plot just a really basic condition. We're going to start with 80 degrees Fahrenheit. And hopefully this isn't the first time you've looked at a psychrometric chart, but just in case it is, I'm going to break this down kind of slowly. So on the bottom of the psychrometric chart, we have a scale for temperature, dry bulb Fahrenheit, left to right. On the right-hand side of the chart, we have the scale for the amount of moisture in the air we're measuring, and that could be expressed in grains and dew point, vapor pressure. There's actually other things we could put there too. On the left-hand side, we have this really weird scale, this curved line for relative humidity, and I'll make all those sense out of all those here in just a second. But we have 80 degrees, so at 80 degrees, we find 80 at the bottom, and this whole line that runs perpendicular up the chart represents 80 degrees Fahrenheit. Our 80-degree air is 40% relative humidity. And what that means is that our air has 40% of the moisture that it would contain at saturation or full. So notice that 40% is kind of in the middle of the chart, but not quite. It's a little bit below the middle of the chart, which makes sense, right? It's just less than half. Using a psychrometric chart where these two lines cross, we would put a straight line across the chart. And this is how we use the chart to make calculations, right? So at 80 degrees and 40%, if we look straight across the psychrometric chart, we could calculate from that the grains per pound. We could calculate from that the dew point temperature, which is that middle scale. We could calculate vapor pressure. And depending on what kind of psychrometric chart this is, we could calculate other things as well. In this case, though, I first want to draw out one really important element. I want you to note that although we have a dew point temperature, and I've got it circled here, of 54 degrees, and we'll talk about what that means here in a second, I want you to note that if that dew point temperature was higher, let's say the dew point was 60 degrees, notice how the grains would also be higher, right? Notice how the vapor pressure on the far right would also be higher. In other words, there's a direct relationship here. Higher dew point means more water, more grains per pound. Lower dew point means less water, fewer grains per pound. And this is the first element of my expression earlier, that you could use dew point and just completely scrap the use of grains per pound for virtually any discussion we would have in water damage mitigation. I say virtually because there is one exception to that rule, and I'll talk about it later. But dew point is an expression of the amount of moisture. A higher dew point means more moisture. A lower dew point means less moisture, right? Just like with grains, higher grains means more moisture. Lower grains means less moisture. So at 80 degrees and 40%, let's get back on track, we have a dew point temperature of approximately 54 degrees. What does that mean? What that means is that there is a certain amount of moisture in the air, there's a certain mass of moisture. And at atmospheric pressure, that mass of moisture requires a certain amount of energy to remain a vapor. There's a certain amount of energy that must be present to sustain that mass of water. The amount of energy that must be present, at least in sensible temperature, is 54 degrees Fahrenheit. That's why the dew point is 54 degrees. Now, you can observe this by looking at the chart. Notice I've shaded in a part of the chart here in white. As you pan your eyes from right to left, notice what happens here on the psychrometric chart. We're crossing different relative humidity lines, right? We're at 40% relative humidity presently. But if I cool the air down to 70 degrees, we would now be at about 60% relative humidity. If I keep cooling it down to about 60 degrees, we'd be at about 80% relative humidity. And right at 54 degrees Fahrenheit, I'm going to give you a second to locate that on the chart because it can give you a headache the first time you look at it. But right at about 54 degrees Fahrenheit, the relative humidity hits the edge of the chart. That's called the saturation line. It becomes 100% relative humidity. If I take that air and cool it down any further, all right, then all of a sudden I've got too much moisture for the amount of energy in my air. So if I go below 54 degrees, I'm going to have moisture literally condensing in the air or condensing onto the surface that's taking the energy from it, which could be a piece of dust floating in the air or a cold outside of a container, but you're going to begin to see the process of sweating or condensation that will occur. In fact, the further I go below 54 degrees, the more of that condensation is going to occur. So 54 is my dew point. Notice on the far right-hand side of the chart, I can calculate 54 degrees as my dew point. On the left-hand side of the chart, I can see that 54 is my dew point by noticing where that amount of moisture crosses that saturation line. Okay. Now, the next layer in this that's going to build into where we're going with dew point. So what does all this mean, Brandon? How do I use it? The first thing I want to touch on is that the further you are below dew point, the further you take air below its dew point, the more moisture it's going to lose, right? We refer to this as degrees of dehumidification or degrees of condensation. This is actually how refrigerant dehumidifiers are designed, right? They're designed to take the air you're trying to dry and to cool that air below its dew point to cause moisture to sweat out onto those cold coils. And they're designed to give you a good 15, 20 degrees of dehumidification. So lots of moisture wrings out of that air. On the opposite side of this, we get the opposite result. When I am above the dew point of my air, it's not condensation that I'm promoting, it's evaporation, the opposite, right? So if I do the opposite, I get the opposite. That's the nice thing about physics. So if I'm above dew point temperature, then I'm going to generate a certain amount of evaporation. We refer to this literally as degrees of evaporation. And we've talked in previous episodes that there's a target for this, right? We want to ensure that we have a target of 20 degrees of evaporation. We like to see that the amount of energy in the air is at least 20 degrees above, that sensible heat is 20 degrees above the dew point of that air. So the surface where I'm drying needs to be 20 degrees above the dew point of that air to sustain that energy. And we'll give some examples here and some applications in just a moment. So that's just a quick recap of what dew point is. It's the temperature at which air becomes saturated, typically through cooling, right? The temperature at which air becomes saturated. It can hold no more water vapor. If I cool air below its dew point, we get condensation, right? We get condensation. If I warm air above the dew point, we generally have the potential for evaporation, okay? So that's dew point in a nutshell. Now, let's get to the practical. As I flip over to the practical, I want to use this as a reminder on our housekeeping here really quickly. If you have any questions on the material that we're covering here today, especially as I now get into some of these examples, don't hesitate to drop those into the Q&A. When we hit the end of the presentation today, as we typically do, I'm going to jump through those questions and answer those live and in time with the presentation. And don't worry about just sticking to the topic either. Any question related to water damage mitigation, even if you want to draw us off topic, I love questions that come out of left field as long as they're related to water damage, and I'll do my best to answer them for you. All right, so with that, let's get into some specific examples. So here we have a structure, right? And I've just kind of plotted a variety of readings in the structure here. The readings of the outdoor air at 60 degrees and 50% relative humidity. And then we have several rooms inside where in some of these rooms we're relatively warm and some rooms were a little bit cooler. We may or may not have a water damage that has occurred in this structure. That's actually kind of a moot point at this particular juncture. Just focus on the fact that we have a variety of different temperatures, a variety of different humidities throughout the space, and lots of different types of surfaces that we're dealing with. And let's kind of zoom in on a couple of these and talk about what dew point tells me in each of these areas. Okay, so first let's take a look at this room that is 80 degrees and 40% relative humidity. It's got a dew point temperature of 54 degrees, and presently we have an outside condition of 60 degrees and 50% relative humidity, which incidentally has a dew point of 42. All right, so I don't know my grains. We didn't calculate grains. I don't know my vapor pressures or any of this other stuff in psychrometry. We only know what we have on screen here. What does that tell us? What do we know? First of all, just from this information, I know for a fact that the outdoor air is drier than the indoor air, and it could be used to lower the indoor humidity. How do I know that? I know that because the outdoor dew point is lower. If the dew point is lower outside, there is less moisture in the air outside. It does not matter that the relative humidity is higher outside. Relative humidity, you have to remember, relative humidity is relative. right? It's relative to the energy in that air. It's not an expression for the amount of moisture. Relative humidity doesn't measure moisture. Relative humidity only expresses the moisture relative to the size of the container, if you will, right? It's like saying that my gas tank is 50% full. You have no idea how much fuel I have if I say my gas tank is 50% full. All you know is I'm holding on to half of what I could, right? So dew point does express the amount of moisture in the air, because the higher the dew point is, right, the more energy is required to suspend that moisture. So it is drier outside than it is inside. It's an automatic. If you open up a door, you open up a window, or give any other means for a transfer or movement of moisture, the moisture will move from inside to outside. It could be 100% humidity outside, and that would still happen, okay, as long as the dew point is lower outside. So that's the first thing that I know, and I know it for a fact. The second thing that I also know is that I do not have a condition that is very conducive for drying, okay? And this is probably one of the most important things to be able to glean from this. It's not a horrible condition, but it's not a very strong condition. And here's how I know this. I have a 54-degree indoor dew point. All right, so the amount of moisture in my building, in the air inside my structure, requires a minimum of 54 degrees to remain a vapor, right? But I have an outdoor temperature of 60 degrees, all right, which means there's only about and I put 14 degrees, it's actually not even 14 degrees, it's a 6-degree difference. So pardon the error on my slide. I'm only 6 degrees above the dew point of that indoor air. What does that mean? Why is that important? So let's kind of dive in a bit deeper. Let's say that as a part of this project, we did have a water damage that has affected the exterior wall assembly, especially if the water originated overhead and ran down through the wall assembly. We have wet 2x4 framing, we have a wet wall plate, we have a wet top plate. We could even have some wet insulation that we're trying to save potentially, you know, if we decided that we were going to save that. If those materials are near the outdoor air temperature, and I'm using the air in the building and injecting that into the wall cavity to dry that wall cavity, then I'm going to be drying building materials that are going to be near or at 60 degrees Fahrenheit, especially if they're the materials adjacent to the outdoor air. When that air moves into that cavity and that air cools down to that temperature near those surfaces, that relative humidity is going to be extremely high because I'm going to be near the saturation point of that air. Remember, that air needs 54 degrees just to remain a vapor. And if I cool the air down to 54, it's going to be 100% humidity. Cool it down to 60, you're getting pretty close, right? That's going to be like an 85% relative humidity. That is not very conducive to drying. And remember, the simple way, if that gets a little complicated and a little muddy when you look at that, remember the simple way to understand that is just make sure you have at least 20 degrees, which means that my 54-degree dew point in my outdoor air of 60 degrees, if I wanted at least a 20-degree delta, the indoor dew point has to drop to 40. Or I have to ensure that that entire wall cavity is at least 74 degrees. Either one of those would give me the 20-degree difference. So I either need to supplement the heat going into the cavity to make sure I maintain that temperature and verify that I am, or we need to drop the indoor humidity. By the way, we can drop the indoor humidity pretty quickly using the outdoor air, right? So not only does it state the problem, it states the opportunity, okay? So that's one example. The next example I want to dive into is down below. We've got a basement here. This is an unfinished basement area, and it's 68 degrees, 55% relative humidity with a 53-degree dew point, okay? We've got, however, many of these surfaces in contact with the ground below grade, all right? And let's say that this grade, this ground that is surrounding this basement area is approximately 48 degrees. So kind of the same discussion here, kind of digging into what the challenges and opportunities are. The first thing is just analyzing again, what is the dew point of my air? In this case, it's 53 degrees. And what is the temperature that I'm dealing with of these materials and surfaces? Now, I'm not necessarily going to know that the ground is 48 degrees beyond the concrete slab, but what I can determine is the temperature of the slab itself and the temperature of the footings, right? I can determine that temperature. And if that temperature is at 48 degrees, and I have a 53-degree dew point for the air I'm using to try to dry those surfaces, again, this is not going to be very effective, right? The delta there, the difference is that I'm only about 5 degrees warmer than the surface. My dew point is only 5 degrees above that surface temperature. I need at least 20. So again, how do I fix this? What's the solution to the problem? The solution is either to ensure that the air's dew point, right, is lowered down to the point that we are 20 degrees below the surface temperature, or to raise the surface temperature, either one of those, until I get to that 20-degree delta, right? Either one of those will work. And this is a really common challenge that we run into when we are dealing with a variety of temperatures throughout a drying environment: outdoor temperatures, ground contact material temperatures, air-conditioned areas and air-conditioned surfaces and the temperatures that they create. You know, you're not going to have a consistent temperature throughout a drying environment. And part of the reason I spend so much time really emphasizing this in today's episode and previous episodes is that we often overlook this. You know, we tend to go into an environment, we grab a moisture meter, we measure how wet a building material is, we take a couple temperature and humidity readings so we know what the affected air is, or maybe the outdoor air is, but we never step back and really appreciate the fact that the temperatures have to be appropriate to support drying. And dew point forces us to have that conversation, especially when we apply that 20-degree delta, right? It forces us to have that conversation. It also makes it relatively simple to ascertain from that discussion whether or not there's enough energy, if we just remember that 20-degree delta. Okay. Take a look at another example here. We've got an upstairs area or a first floor area over a basement area. 80 degrees, 40% and 54-degree dew point. Down below, we are at 70 degrees. So the delta here is going to be somewhere around a 16-degree delta. Where do I get that from? I get that from the fact that we have a 54-degree dew point in the upstairs area. That's how much energy is required. If this flooring was wet, if that's what I'm targeting in between the two, that's a 70-degree temperature. So at a minimum, those flooring materials are going to be at approximately 70 degrees, which is 16 degrees above dew point. Closer to that target, much, much closer to that target than the other conditions that we looked at. Ideally, however, we would still hit 20, okay? All right, so that's just kind of walking through just one really basic environment and taking a look at kind of a mix of, the different conditions that we can encounter commonly in an environment and how we might apply those. Now let's make this a little bit more extreme. Right, I was using very, very basic outdoor temperatures, a moderate outdoor temperature, but let's look at this one. It's a bit more extreme. And now I just want to really simplify matters and just focus on the numbers in blue. Okay, just focus on the numbers in blue. Outside, we have a 36-degree temperature. So now we're talking about much colder, maybe a winter temperature for some of you. And inside, notice the dew points that we're dealing with. 54, 54, 53, 55, and just understanding what we've talked about to this point, this should raise a really big red flag for you, right? A really, really big red flag. And if all that today's discussion does is get you to recognize that one red flag and the fact that this is going to be a problem in this drying project, it's going to be a problem on all of the surfaces in contact with the outdoor environment, whether that be exterior walls and footings or attic areas or whatever else it is, a crawl space and a subfloor, then we've made a huge stride forward for you in increasing your potential to dry in these types of circumstances. By the way, before I go further, this is how this normally plays out in a project. Very typically what happens in a project like this is that we start with higher humidities, obviously, initially, because there's a lot more moisture in the building, and this cold outdoor air temperature. And what we observe in a drying process is that we have several areas that begin to dry, and typically those are all of the surfaces that are not in contact with the outdoor environment. And all of our surfaces like wall plates and edges of subflooring and wall cavities and things like this, they either remain at the same level of moisture or potentially even increase in moisture content slightly until all of the other materials that are not in contact with those areas begin to dry and start releasing moisture. And then our evaporation rates really slow down, the indoor humidity begins to decrease, and we go from 80-40 inside down to 80-30 or down to 80-25. And as that indoor air begins to become drier, the indoor dew point begins to drop. And then once we get down to an indoor dew point of like 20 degrees, all of a sudden everything else that was cold begins to dry. Right? Wouldn't it be nice if I didn't have to wait 2 or 3 days for those more difficult materials because they're cold to begin to dry? And we identified this problem right up front. And these challenge areas began drying at the same time the rest of the building does, right? And instead of 5, 6, 7, 8 days where most of that time is focused on these problem areas towards the back end of the project, if those were drying in concert or in synergy with everything else. So again, this helps me identify that challenge, because at 36 degrees outside with a 54-degree indoor dew point, those exterior surfaces or those materials in contact or influenced by outdoor air temperature, they're not going to dry. They're going to become wetter, right? And over the first 24 to 48 hours, you're going to notice either a flat moisture level or an increasing moisture level in those materials and surfaces. So to really drive that home, let's bring it back to the psychrometric chart. And this will be kind of our last example here to really drive home dew point by looking at this one more time. As I do this, again, I want to remind you, if you have any questions that you want to drop into the chat, make sure you're doing that now. So here we have, again, 36 degrees outside, 80 degrees, 40% relative humidity inside. Let's plot this on a chart and understand the problem from a psychrometric perspective. So again, 80 degrees, 40% relative. We can see the calculation there on the psychrometric chart. We've got a dew point of 54 degrees. Now notice my 36-degree outdoor temperature. I'm going to plot that also on the psychrometric chart. Okay. Notice that my 36-degree outdoor temperature meets that calculated moisture content line from the inside of the building. It meets it off the chart. That's the first indication that we've got a problem, right? So any of this air in the building that moves inside of that wall cavity and cools down close to the outdoor air temperature, all of a sudden it's going to have more moisture in it than the air can support. And guess what's going to happen to that moisture, right? That moisture is going to condense. It's going to sweat out onto those surfaces. Those surfaces are going to become wet. They're not going to get drier, right? They're going to become wetter. So the amount of moisture we have in the air inside the building is too great for the surfaces that are going to be anywhere near that outdoor temperature. In fact, any surface that's below the dew point, which is 54 degrees Fahrenheit. Okay, so that's dew point. That's how dew point can really assist in the process. That problem is going to exist throughout that entire exterior wall assembly. And again, I've highlighted it here on the slide, but this whole area of that assembly, all of that is at risk for being at some degree colder than the indoor temperature because of how cold the outdoor air is. And the more I move through that assembly and closer to the exterior, the more we're going to meet that exterior temperature and the worse the problem is going to become. Okay, so a couple of things here kind of in closing and in review. First and foremost, the most important thing I want to drive home about dew point is that dew point is a tool, it's a metric that you need to use, right? We have lots of documentation that we do simply because that's what's on the form, right? The form asks me to record temperature and humidity and grains per pound in the affected area and outside and things like this. And that's well and good, and there's purposes for that documentation, and we get lots of value out of it. But at least understand dew point. When you're calculating your indoor readings, especially where you're affected, and that's where they're going to be highest, at least calculate that dew point. At least understand what that dew point is. And let's say the dew point's 55, whatever it is. And at least ask yourself one basic question. Is there a risk this air could be cooled below its dew point? Is there any risk for that? Consider your outdoor temperature. Consider if it's a basement where it's cooler and you have cooler surfaces. Is there a risk that this air could be cooled below dew point? If there's a risk, measure it, okay, and verify, is this going to happen? If it is, prevent it now, right? Lower the indoor humidity, raise the temperature of those building materials. You have lots of options in that regard, but be aware of the problem, address the problem, okay? At a minimum, that's the first thing I really want to beg of you as an action. The second thing is if you want to go from just avoiding problems to actually drying a building, the next thing is will all of my materials that are wet be at least 20 degrees above that dew point? If I got a 55-degree dew point, everything I'm drying should be at 75 or warmer. So is it, right? And if it's not, how do I get it there? Or how do I lower the dew point of my air? Okay, one of those two. All right, so those are kind of my calls to action for you, is that if you can just apply those two principles, you will dry structures more efficiently, more effectively, more rapidly, more completely, and avoid potentially causing some damage in circumstances where condensation is occurring where you're not even trying to dry, right? Just by understanding I've got really humid air, it's cold outside, I'm going to get sweating in my exterior assemblies if I blow this wet air into wall cavities, and all of a sudden I'm going to get sweating on surfaces that weren't even wet to begin with, right? They aren't even on my radar. So it's really important to, again, just to understand, at least calculate dew point and consider your surrounding temperatures. Having said that, here are the things that I want to review, okay? So in review, water content can be expressed as dew point, right? So if I just know the dew point, if it's 55 dew point indoor and it's 43 dew point outdoor, I know the outdoor air is drier. So you can literally supplement grains per dew point. The second is that dew point also indicates the drying capacity, right? The warmer a surface is above the dew point of the air you're blowing across that surface, the greater the drying capacity. Target a minimum of 20 degrees. I think I've said that at least 20 times today, but target a minimum of 20 degrees. And then finally, last but not least, that 20 degree is a minimum, right? It is an absolute minimum. If you can be more than 20 degrees above the dew point on the surface, wonderful. It'll dry more readily, okay? So in review, again, grains per pound, you can literally make the same deductions with dew point. The only difference between, or the only exception to that rule, which I said earlier I would share with you today, is when we're trying to calculate grain depression on a dehumidifier and understand the water removal over a certain period of time. If you've attended previous Technically Speaking episodes, we ran through a formula on that. CFM times grain depression divided by 71, you may remember. And that calculates pints of water removal. In that case, I really need grains. Outside of that, any other discussion I would have in psychrometry about where am I wet, where am I dry, where is there more water, is the water content decreasing day 1, day 2, day 3? I could have all of those conversations using dew point alone. Okay. All right, so that wraps us up on episode 10, If We Only Learned Dew Point First. I don't see questions in the chat, so as I go through kind of my wrap up here, I'm going to remind you one last time, if you've got anything you want to throw at me for a question today, please drop those in now while I close out the portion of this that'll be available as a recorded webinar. A couple things here I want to close out with. First of all, again, my name is Brandon Burton. I am the chair of the ANSI ICRC standards and here to support you in any way I can in this industry. My email address will come up here on the slide in a moment. Please note that down if I can be of service. This was episode 10, If We Only Learn Dew Point First. Next up, episode 11, we're going to start taking all of our episodes and really honing those down into highly technical mitigation reports. How do I take this technical content, all these things that we've learned over the course of this year through the previous 10 episodes, and really wrap that up into a technical report, especially in a way that I can use with folks that don't necessarily understand all this psychrometry mumbo jumbo, right? How do I translate that into documentation that can be useful? It'll be a really fun session, so I'll give you some specific examples in documentation and how I would use that personally to communicate some of the, kind of the wins of my mitigation effort and really take credit for the effort that I've put into a drying project. So that'll be episode 11. After that, we're going to wrap up the year in December with episode 12 and really review all of the best kept secrets for all year. I want to note, by the way, that we're already beginning our series for 2023. And what we're going to do in 2023 with Technically Speaking is we're going to branch out of water mitigation. We'll still have some really fun water mitigation topics, but we're also going to pull in fire damage restoration, mold remediation, even some reconstruction topics. So we're really going to branch this out and touch other areas in your business and probably some other divisions in your business. By the time we finish episode 12 in December, I'll have that schedule published. I've also got some really fun and exciting guest presenters that I plan on pulling in. I've got a lot of really good contacts in the industry that I've worked with over the last 30 years that are experts in different areas of mitigation that I frankly am not. So I'm going to pull in some of those experts as we talk on fire, for example, and talk about some of these other topics that will bring in some great Technically Speaking content for you. So look forward to that in 2023. Also note that you can view any of this year's Technically Speaking episodes by going to restoration webinars here at nextgearsolutions.com. You can even still earn the CEC credits for any of those episodes that you missed. The only thing you won't get in the recordings, you won't get the Q&A session here that we're about ready to jump into. And then last but not least, the final thing here I want to throw in before we get into Q&A is do note that we have Interconnect 2023 coming up. And this is our event that we hold annually. Next year did it under a slightly different name. CoreLogic had done it under a slightly different name. And now that CoreLogic and next year are one and the same, we are having the first major event of the two organizations combined, which is Interconnect. It's going to be in Los Angeles. It's coming up in January. Go to interconnect.com to get more information about it and to register for the event, and we'll see you there.